which is what is called as your, no, in this case, it is a 2-floor building. So we say that's a ground floor plan, right? That is a top view, but cross section of the top. Then it is interesting because now you can see how the rooms are laid out, how the walls are, doors, windows, and so on. So cross-sectional views are very important part of, let us say, engineering per se and engineering visualization. That is what the course is all about. And today we'll talk about what are the rules of the game for creating cross-sections, which are not confusing. Right? So everyone understands what this section is all about. That is today's class. Now let's look at why do we need that, okay? And we already looked at some of the objects where there are internal features. Let's say there is a cylinder with a hole, and in the front, let's say a vertical cylinder with a hole, vertical hole. If you see the front view of the cylinder, then you do not see the hole. You just see a rectangle of the cylinder, projectional cylinder. But then we were showing the hole by the means of dotted lines. You remember that? Now that is okay if there are just a simple few hidden views or hidden features of the object. But moment there are many hidden features or features which are not visible from that particular view, okay, then it becomes little difficult to visualize how the object is. And that's the reason why we show the so-called cross-sectional view of the object. So if you see in the example on the right side, that's a typical what's called as a lug, right? I mean, you have a hole and then you put some, let's say, a shaft to that, and there's a lug. So usually it is to connect two different mechanisms, in a machine, let us say. And you see a 3D view on the top, you see the top view below that. But if I show the front view of that, which is very similar to the top views, what you see in the 3D view, just the front view of that, I mean, nothing interesting. But if you show a cross-sectional view, you can actually see a few features like, for example, hole in the middle, right bottom, and things like that. So that's why cross-sectional views are important. Even this example is a simple example. This example, even if we had shown the hidden lines, good enough. But as you go more and more complex objects, then we'll realize the value of the cross-sectional views. How do you get the cross-sectional views? We cut the object by imaginary plane. The plane could be, of course, horizontal, vertical, inclined, which we'll talk about in the next slide. So we cut the object by an imaginary plane, and then in throw away, again, the throw away means not really throw away, not really cut. We are doing an imaginary cut by imaginary plane, and imaginarily you're throwing away a part of the object, and then you're seeing the cut section, cross section of the object, and you're drawing that. Okay. So typically, what kind of problems that we will be doing in this exercise? Two kinds of exercises. One is given an object, draw the cross-sectional view. Okay, or given the view of the cross section, find out where the sectional plane, the imaginary cutting plane is, right? First one is more important. Second one is also important in some cases. So we'll talk about both in today's class. So far, so good. Okay. Now, what kind of a cutting planes? And before that, also the what is the rules of the game, nomenclature. So you remember we already talked about the center lines, right? I mean, line, dot, so on, right? So how do we know? Finally, you have an object line, you have a hidden line, you have, we are going to have cross-sectional lines. So not to be confused about all these things. So what we do is for a cross-sectional line, it is a long dash and a small dash, long dash, small dash, not a dot. Okay, because a dot is used for center line. Also, the entire line is of not same thickness. Okay, the part of the section plane which is outside the object, we draw a little bit thicker line so you can see where exactly it is. But inside the object, and that's not happening in this place, right? I mean, what you're seeing is inside the object is also same thickness. So this is not correct. But when you draw, and we'll show you more examples where it is correct. Inside the object, the sectional plane is with a thinner line. So now you start looking at the importance of having two different pencils. Okay, one pencil with a thicker line or thicker thing, or a thinner pencil. Either you sharpen the pencil like that, or if you are using those standard pencils like Staedtler and Indian companies, you can buy two different pencils. One pencil with, let us say, 0.7 or 0.75 millimeter lead, and one pencil with a 0.5 millimeter lead. So the 0.5 millimeter lead one can be used for the inside portion of the section plane. Similarly, even the cross-sectional view, which you have to draw the cross-sectional lines, those lines have to be thinner lines. The outer boundary of the object, okay, will be thicker line. But the cross-sectional hatching, what we call as hatching lines, cross-hatching lines, they will be thinner lines, and they are always at 45 degrees to the horizontal or vertical. Okay, so that's the rule. And what is sectional view is what you see in the bottom picture as the hatched portion of the thing, along with the whatever portion of the object is still visible. You're throwing away, let us say, the front part of the object, so that is removed. But the back part of the object is still there, along with the cross-sectional view. So the entire, let us say, front view or top view of the object, along with the cross-sectional view, is called as a sectional view. Section or sectional view, both are same things, is called like that. Okay, so this is the basic rules of the game. But how do you draw the lines, line thickness, the line type, and things like that. Now let us start doing a bit of a analysis of what kind of sectional planes can be there. I'll go easy on this slide until you are very clear about it. So here the sectional plane is the plane which you see outside the object. What is object here? Object is a square, right? A cube, let us say, or a rectangular square, rectangular block. So what you see as a rectangular block here is your object, but it is now cut. There's one plane which you see outside the object with indicated by dots. Okay, the dots indicate the sectional plane in this particular picture. So the object is cut by sectional plane. Sectional plane can be four options: perpendicular to the horizontal plane, parallel to the vertical plane. What you see in the first option here, or reverse of that.
Excuse me, sir.
Yeah, go ahead.
Sir, can you explain how is this section plane outside the object? Like I didn't understand this line.
How is the
sectional plane outside the object? What does it mean by?
I'm sorry, I made a typo, visual oral typo. It's not outside the object. It is indicated. The boundary of the sectional plane is indicated outside. So basically, this is the plane you're looking at, but it is not outside the object. So I should correct myself. The section plane is actually cutting the object. If sectional plane is outside the object, completely outside, it is meaningless because you don't see any cross section in that. So thank you for that saying that. It's just that the boundary of the sectional plane has to be shown outside the object. That's what I meant. Okay, but it is actually cutting the object. So it is going through the object. Okay, thank you for that. So this plane can be either parallel to horizontal plane, perpendicular to horizontal plane, as you see in the first example, parallel to vertical plane, or reverse of that, perpendicular to the vertical plane and horizontal to the horizontal plane, parallel to the horizontal plane, or I can make it slightly more complex. What you see in the third example is perpendicular to the horizontal plane but inclined with respect to the vertical plane, or reverse of that, which is perpendicular to the vertical plane but inclined to the horizontal plane. The question is, why do you want to do these inclined planes, right? So inclined planes you do only when you want to see the true cross-sectional area. So when you, and we'll come to that example also a little bit later. Like in the previous examples where we talked about the auxiliary planes. Remember auxiliary planes? Okay. Why did you want to do auxiliary planes? Because you want to see the true shape of the object. Now you're talking about true shape of the cross section. Same reason for this also. Okay. But you'll see examples of that. It will be a little more clear. In this particular slide, you only need to remember and mentally visualize the sectional planes, because next few slides will show you the sectional planes and what happens and how do you draw the cross-sectional views. Let's start looking at one example here. Let's say this object is given to you, okay, and then we say that let us draw the top view, normal top view, but cross-sectional front view. So what you're seeing here is the top view, normal top view. This is how the object is. I'll give you a couple of seconds to maybe figure out. So you have the base, which is rectangle, let's say square or rectangle, that is outer shape of this whole object. Then you have this semicircular portion, which you see from the top view. It will come up as one more rectangle here. Okay. Then you have this another semicircular portion, which is smaller than that. That is this third rectangle here. And then you have the inclined, it's called as a rib, right? Because this rib is basically used to strengthen this, what's called as a boss with a hole, right? This is called as a boss. Okay. boss, but it's double meaning here. Boss is basically something which is a portion which is projecting on a surface, and then boss itself has a hole, and then this boss is connected to the base by this rib, basically to strengthen the whole boss and the rib and things like that, base and all. So this is shown as a fourth rectangle here. And the dotted lines are showing you this hole which is going all the way through and through. See, if that this dotted line is not there, you would never know that this hole is going all the way through. Correct? And then we have another line in the middle, which is the center line of the hole. Right? This line, which is center line of the hole, should be line dot line dot. Okay? And then additionally, what you see is a cross-sectional plane which is outside the whole thing. And where is the cross-sectional plane? We are going to draw the sectional front view. Okay, so the cross-sectional plane is horizontal or vertical. And where is it located? It is right located to the middle of the object. Okay. Now just imagine how the cross-section will look like. First of all, imagine how will the front view look like. We're talking about cross-sectional front view a little later. Front view, how should it look like? It should look like an L shape, right? If you see front view, L shape all the way to this height. And then you see this projection of the boss and an inclined rib, which I talked about. But a cross-section through the entire a vertical plane, right? Perpendicular to the horizontal base. I talked about this whole thing. L shape is this L shape, and then you have this rib here. Okay, but when you cut this whole thing, okay, you see so what do you see here? One is this section here, the top section, bottom section, and you also see this is a center line of your hole, and then you see this entire cross section, which is L part, including this part below the hole, above the hole, you see these two portions. Now, why is this not cut here? Okay, depends on where you're looking at. If you look at this view here, okay, this arrow here, arrow is telling you from which direction you're looking at and which portion of the thing you're going to throw it at. Okay, so this is how you're seeing this. Because the back portion is still there, you can look at this portion also. Take it now. How do you draw the whole thing? Okay. And please imagine this step by step. We are not talking about object without any internal features. Let's make it very simple to start. So you have the same cube here. We have the same sectional plane here. The cube is now turned. It's not parallel to the horizontal or vertical plane. It is with respect to the vertical plane. One of the faces is inclined at 30 degrees. Okay, and sectional plane's location is given to you. It is parallel to vertical plane and 9 millimeters away from the cube axis. So let's say cube axis is the intersection of the, let's say, the two diagonals. So 9 millimeters away from the axis of the cube, and it is further from the VP. It is which side of the axis? Towards the away from the VP direction, VP vertical plane. And then now we have to draw the sectional front view and top. How do you do that? Let's first of all assume the section plane is transparent and cut portion of the cube is removed. Let me draw the front top view first, because that's all of you know that. You know the cube, so it will look like a square in the top view. And we already said it is inclined at 30 degrees to your XY plane or vertical plane in this case. So you can draw this ABCD, you know how to do that. Now, we want to not draw the front view only, but the cross section of the front view. How do you do that? Where will the cross section be? It won't be here, right? The cross section is where the cut section is cutting this. Where is it cutting? It is cutting at point 1 and 2, intersection 1 and 2. So the sectional plane which you see, the front view of that will correspond to this 1 dash, 2 dash, 3 dash, 4 dash here. But although we are seeing the cross section from the direction, view direction is here, the back part of the cube is still there. And that's the reason why the back part, you see the A dash, C dash, right? This is the outer part of the cube is still seen, and that is not cross section. I'll just keep it for 30 seconds so that if you have any doubts, we'll clear it right now. Because if you understand this, then the remaining steps are easy. If you don't understand this, then we are in trouble. Anyone has any doubt about this? I'll wait for 30 seconds. Or you mentally map to what I said just now, right? I'll just go back on animation once again. We talked about the cube inclined to vertical plane. We talked about the cross-sectional plane, and plane is away from the vertical, away from the 9 millimeters from the axis of the cube and in the direction away from the vertical plane. We drew the normal front view. That is what, I'm sorry, it says sectional front view. That is not correct. This is actually front view and sectional top. Sorry, sectional front view and top view. I'm sorry. Okay, sectional front view, but normal top view, which is what you're drawing here. But we draw the top view first. Draw the sectional plane because sectional plane is distance of from O to HT, the horizontal trace of the sectional plane, right? HT is the horizontal trace of the sectional plane. This HT, horizontal sectional plane, is 9 millimeters away from the axis of the cube. So this we are drawing HT. Once we draw HT, we know the intersection of HT with this, the drawn top view of the cube, and then we project it to the front view. Normal front view is AB, AC, A dash, C dash, G dash, and E dash. That is your A is A dash, and your C is coming here. That is okay. And C and G are same place. Okay. But the cross-sectional view is where you get this 2 and 3, which is 2 dash and 3 dash, and 1 and 4, which is 1 dash and 4 dash. I think it is fairly obvious. Yeah.
So can you repeat what was this HT?
HT is nothing but how the sectional plane is seen in the top view. We talked about horizontal trace of those auxiliary planes. You remember that? Same as that. Horizontal trace is nothing but the cross-sectional plane seen in this case the top view. And how it will look like top view, because it is perpendicular to the top view, it will look like a line, and that HT is a line, nothing but the cross-sectional plane. Clear?
Okay, so like whenever we have to show this cross-sectional view, like from the when it looks like a line, so it is a convention that we name it as HT, right?
Yeah, and similarly, if it's a vertical plane, you call it as a VT, vertical trace. We already introduced these terms in the auxiliary views, right?
Yes, sir, actually, but there were just points. So HT and VT were points.
Yeah, correct. Because now this sectional plane, although we have put a boundary here, so that otherwise we will not know where the plane is, right? Supposing I have not put this boundary in sectional plane, how will you know there is a sectional plane there? Correct. So therefore we have to put something. HT is H and T can be anywhere. Thank you for saying that. Okay, it's an infinite sectional plane. You can say that. But to represent that, so that we understand that it is represented as a line. That's why I said it is outside the object, right? But outside doesn't mean that it is only limited by this. It can be infinite plane, not going through the object.
Okay, thank you.
But thank you. All doubts are welcome, by the way. It's always good to have that. So now one interesting thing is that the 1 dash, 2 dash, 3 dash, 4 dash in the front view, it is the true shape of the cross section, in the sense that this cross section which you see in the left picture, the true cross section, whatever it is, okay? And what you have drawn here by this exercise, this 1 dash, 2 dash, 3 dash, 4 dash, is a true cross section. It is not distorted in any way. Why? Because your cross sectional plane is parallel to the vertical plane, and when it's parallel, the projection is same as a true projection or true cross section projection. Both are same. If the vertical plane was inclined, then what you see in the projected cross section would not have been same. In fact, projected cross section would have been thinner, less wider than the actual cross section. So that is also clear to you. And just to reiterate once again, the part views, which means A dash, the line from A dash, C dash, G dash, B dash, should be drawn by a thick line, and even this cross-sectional view, which is A dash, 1 dash, 4 dash, and 2 dash, 3 dash, also will be dark lines because they are object lines. But inside this cross-sectional hatching, what you do, that you would basically do it by a fainter line or thinner line. Okay. Sometimes if you do not have let's say, two different pencil thickness, what do? You have the same pencil thickness, for example, you're in emergency, you don't have two thicknesses, and you can't be sharpening the pencil for cross-section again, thickening that for outer views. So in that case, what we sometimes suggest is we have two different types of pencils. You can have what's called as a B or a 2B, which is a softness of the pen of the carbon or graphite, and you can have a hard, which is H or 2H kind of a thing. So you can use a H, which is a hard pencil, which will be fainter automatically for drawing your hatching, and a soft pencil, which is a darker, that you can use it for your outer lines and so on. So that's why the fainter lines, the faint could be either in terms of the darkness of the line in an emergency, but ideally it should be thinner lines. Okay, so either way is possible. But please do have, in my opinion, two different kinds of pencils. You can have HB pencil, which is a classical standard HB pencil, about 0.7, 0.75 thickness of the line. And you have a H pencil, sharper pencil, which is for drawing your cross-hatching lines, as well as your central lines and things like that. Okay. Now we'll look at now sectional plane, which is perpendicular to the horizontal plane, but inclined to the vertical plane. Okay, similar to previous one, but now it is inclined. And let's look at the problem first. So cube in the same position as problem 1 is now cut by a sectional plane, which is inclined at 60 degrees to the vertical plane. Sorry, to the, what did I write here? Some mistake here. 60 degrees to the vertical plane and parallel to horizontal. A typo there. So the face will make 60 degrees angle with the vertical plane is cut in two equal halves. Now, what is it saying? The face making 60, a lot of typos here. So let me just go back to this thing. Basically, in this particular one, I'm introducing now the need for an auxiliary, let us say, sectional view to get the true shape. Because just look at the picture on the left side. Don't worry about angles and things like that. But this phi is what we're talking about is 60 degrees to the vertical plane. Okay, this vertical plane, this is a cross-sectional plane. This is at 60 degrees to vertical plane. That's clear. Now, when you project it, the cross-section is this one, right? When you project it onto vertical plane, obviously the projected cross-sectional view is much smaller than the actual cross-sectional view. To solve the problem of I want to see the actual cross-section, not a distorted cross-section, how do I do that? We can introduce the concept of an auxiliary, look at the sectional plane, okay, or two sectional plane. How do you do it as a two sectional plane? We draw a view which is obviously or take a plane which is an auxiliary view which is parallel to your cross-sectional plane, very similar to your auxiliary view. How do you draw that now? First, you draw the standard top view, which is your ABCD, and a standard cross-sectional view, which is 1 dash, 4 dash, F dash, 1 dash, 2 dash, 3 dash, 4 dash. That's a cross-sectional view. How do you do that? Just figure out for a second. Don't look at the inclined cross-sectional view, which is a true cross-sectional view. We'll look at it a little later. First, you be clear about the top view, right? ABCD is clear because it is at 60 degrees to your, ABCD is, I'm sorry, okay, that's what. ABCD is, the position of ABCD is, TS, position of ABCD is given, I'm sorry, it is same as the previous example, which is your inclined 30 degrees to vertical plane. Okay, same example as that. So it's the same ABCD, this angle is 30 degrees. So this is same, this ABCD is 30 degrees, not phi. Phi is 60 degrees. Am I clear? No confusion there. CD line is inclined at 30 degrees, same as previous problem. So ABCD is drawn in the same way as previous example. Now, and so I can always draw its projection on the on vertical plane, which is A dash, C dash, G dash, let us say E dash here. Okay, that is your projected outer view of the front view. Now we are defining also the cross-sectional view, a cross-sectional plane. What is a plane? It is at 60 degrees to the vertical plane, and it is cutting the face, this face, which is AD face, at equal half. So basically, we're defining the point 1 or 4, right? Because 1 or 4 is same as the your HT is the horizontal trace of the cross-sectional plane. Okay, the horizontal plane is cutting your object. The top view of the object is ABCD. How is it cutting? How do you know the location of the cross-sectional plane? It is at a location where it is cutting your face, AD. You can say ADEH because ADEH actually is a whole face, but then A and E are coinciding, D and H are coinciding into one line, which is AD or EH is one line. That line is bisected by your cross-sectional plane. Is the problem definition clear to you? Then we know exactly the location of the cross-sectional plane. So draw the front view, draw the location of the cross-sectional plane, horizontal plane, its horizontal trace, which is HT. And then now that you know HT location and its intersection with the object, once you know the intersection at 1 and 4, and this line is drawn, you know the other intersection point, which is 2 and 3. And once you know intersection point, we can draw the projections from the point 4, which is 4 dash here, or point 1, which is same as 1 dash here. And then therefore you get your 2 dash and 3 dash in similar way. So this 1 dash, 2 dash, 3 dash, 4 dash is the apparent cross-sectional view of the object. Why I'm saying apparent? Because it is not the true cross-section view. That is how it looks like in the front view of the object. But we are interested in the true cross-sectional view. How do you do that? Obviously, you'll have to draw another vertical plane, which is now parallel to your horizontal trace, which is now x1, y1, similar to your auxiliary views. So x1, y1 is the horizontal plane of the auxiliary sectional plane. And on the sectional plane, if you draw projections again from 1, 4 perpendicular to HT and 2, 3 perpendicular to HT, and you know the height of the object, right? It's already given. Whatever previous example, height of the object is given to you. And that height, if you map it as 4 double dash or 1 double dash or 3 double dash, 4 double dash, same height, you know the points 1 double dash and 2 double dash. And therefore, if you join those 4 points, you get the true cross-sectional view of this object as a auxiliary, you can say front view or an auxiliary cross-sectional view. Now I'll pause here. Anyone has any doubts? We'll clear that first.
Sir, I wanted to confirm one thing. Sir, did you say that this HT line is passing through the midpoint of AD?
Yeah. That is how
sir,
it is.
But like, okay. So like we would be just given the inclination, but then to decide the position, we by default take it as the midpoint.
Slightly repeat. Let me see if I understood your question once again.
So, like once we draw the top view of the cuboid, then we have to place this HT line, and for placing it, we only know its inclination, which is 60 degrees. So
Yeah.
to get the position where to place it, so by default, we choose this midpoint.
Not by default. It is defined like that in this particular problem. The problem could have said that it is not bisecting but trisecting, or it may say that it is passing through a distance from, let us say, 5 millimeters from the point D. No. Finally, you can't draw a plane, cross-section plane, unless you know where exactly it is, right? So you can, it is in this particular case, it is defined saying it is inclined at 60 degrees to the vertical plane, and it is passing through the middle of this face.
Okay.
So it can be defined in different ways. It can be defined in different ways in different problems, right? But it has to be defined. Otherwise, how do you know where HT is? HT could be anywhere, right? 60 degrees could be anywhere, right? It could even be passing through, some problem will say it is such that it is passing through the point D or point E, whatever it is, right? It could be like. And so this point, the 1 dash, 2 dash, 3 dash, 4 dash, this cross-sectional portion could be anywhere, right? Depending on where the portion is. And the length of 1 dash, 2 dash will change depending on where it is cutting, right?
Okay.
But I could have even define a problem that you find which place HT is where the cross-sectional area is maximum in the front view. I mean, you can define the problem differently. In fact, I would encourage all of you to not just look at this problem and only just look at how it is drawn. This course is about visualization, right? Just think about what will happen if HT passes through D, right? Then what happened if he passes through D, instead of having the cross-sectional view, the cross-hatched portion only in the middle of the overall ABCD or ACDG, whatever, it will go to one side, right? If this cross-sectional plane, let us say, passes through, let us say, through D, then this entire right-hand portion from this line would become cross-hatched. One side will be plane, one side will be cross-hatched. Here it is coming in the middle of that. There is a portion of the cube both on this side and that side which is visible. So just don't just look at one example, but also keep thinking about it in different ways. Anyone else has any other doubts about this particular thing? If you get this right, then we are kind of 50%, 60% done with this today's class. Yeah, no question, no answer, no questions. So I'll go to the next one now. And maybe now you do your own thinking, right? Little bit, try your own. So what is the problem? The problem given is a square prism resting on the horizontal plane. Resting on the horizontal plane is not floating in the air. Okay, resting on the horizontal plane, and one of the faces at 30 degrees with the vertical plane. This angle is 30 degrees. One of the faces, any one face, it doesn't matter which one, right? Even this face you can 30 degrees, fine. And it is cut by a sectional plane which is parallel to the vertical plane and x millimeter from the cube axis. This one, this line, okay, where the arrows are seen, and you're seeing from the front of the object, from the bottom part side of the object. So if you see from, I should have done this, my laser pointer, I forgot. Sorry about that. Okay. So if you see from this side of the object, this is your cutting plane. Okay. And where is the cutting plane? It is parallel to the vertical plane. So obviously the trace of that will be a line in the top view. This is what this is. And it is some x millimeter from the cube axis. If the cube axis is O, then it is some x millimeter. X could be anywhere. Okay. And of course, we can also say additionally say that x millimeter on which side of the cube. X millimeter on this side or on this side. That is not said in the line here, but you can say it is away from the vertical plane or towards the vertical plane. You can say whatever it is. In any case, the rules of how do you draw that will be more or less similar. What is the problem here? Given, draw the sectional front view and its top view. Top view is already drawn here, ABCD, but just draw on your sheets or your notebooks. How will the cross-sectional view of it? This will be look like. So you have to actually draw the cross-sectional view where it is intersecting here at 1, 2, and 3, 4. But draw it once, and then so you kind of know how to do the whole thing. To draw the cross-section view, you have to draw all the things by the way. So let me give you maybe 1 minute to do this, and doesn't have to be measured. Just quickly draw by hand. Don't even use a scale and things like that. Just with your hand, draw your your outer thing. Of course, first you draw the top view, ABCD, then you project it, draw the front view, and then you draw the cross-sectional. Do it quickly, 1 minute maximum.
Excuse me, sir. I just had a doubt I wanted to clarify.
Yeah.
In these, when we draw these sectional views, is there any distinguishing factor that we have to add apart from the numbering? Like in the previous ones, these have been shaded, right? So we don't have to do any of that, do we?
The last line I didn't get it. What exactly should or should not be there? What are you asking?
No, sir, here we've shaded, like the sectional views have been shaded, right?
Yeah.
So do we have to shade it when we draw it?
Yes. Otherwise, how will you know it is a cross-sectional view? Otherwise, it will look like a feature of the part, right?
Okay, sir. Fine.
It has to be drawn, and it's always at 45 degrees. So if you notice this particular one in your auxiliary sectional view, it is not 45 degrees to the edge of, let's say, 1 double dash, 2 double dash. It is 45 degrees to your drawing sheet. Correct? Just remember that point also. But
okay, so 45 degrees Y line.
Yeah, 45 degrees to your drawing sheet. Okay, and of course we have a little bit of choice of the distance between the cross hatching. Okay, but make sure that it is not too fine, that is more trouble for you, nor too far away so it doesn't look like a cross section. So there will be some balance of the distance between the cross hatching lines, right? I think if you go back to the book, there may be some rules of even how much far it should be there. Anyone tell any rule is there about how much distance between the cross hatching lines? Anyone knows this? You can put on the chat box if you want.
Sir, can you repeat the question? Just
I mean, my question was that in the cross hatching, when you draw the inclined lines, 45-degree lines, the distance between those 45-degree lines, is it somewhere defined in some rule book? Anyway, let's keep completing your exercise. We need to move forward. So I hope you are drawn by this time. So your top view, of course, same as that, 30 degrees and all that. But now from this 1 or 2, which is the intersection of the sectional plane with your object, you draw the projection line, which goes all the way through this thing and all the way intersecting the top view. How do you draw the top view? The base is resting on the horizontal plane. So this cube is coinciding with the XY line, and you know the height of the cube. Okay, some height is given to you. So you can draw this A dash, E dash, G dash, C dash is drawn to you. And from these projection lines, you get this 1 dash, 2 dash, and 3 dash, 4 dash. And that portion basically you do cross hatch. Okay, so straightforward. If you've done it, congratulate yourself. Now we'll go into a little bit more a different kind of a problem. Okay. The problem here is the reverse. Same square prism. Okay, let's say the base is 1.6. By the way, this double dash on the top means inches, right? In Indian way, you talk about millimeter, centimeter, meters, and so on. But Americans they still use inches. So once in a while, you will come across 1.6 inch, which is represented as a double apostrophe. Okay. So let's say whatever, you can call it 16 millimeters if you want to call it, that doesn't matter. So let's say it is the base of that is given to you, which is 1.6 inches. And it is sitting on the horizontal plane. And all edges of its base are equally inclined to vertical plane, which means angle of this, any of the edges is equal to vertical plane. When you say equal, obviously, it becomes 90 by 2, which is 45 degrees. So it's a very simple example. And when you project this object, top view of this, that is the top view of this, and the front view of that, remember, the base is coinciding with your horizontal plane. So that is your XY line. So your E dash, G dash is sitting on the XY line. And the height is given to you, which is 1.3 inches. Interestingly, if you look at this middle line, which looks like a bisector, which is bisector, it is nothing but your, as you see this B or F, right? This point, B is the top point and F maybe is the bottom point. This one, this whole line, which is BF line to the bottom, let us say, this will come up as a vertical line. And this line represents not only the front edge where the two faces are meeting, but also the back edge. Of course, back edge can be drawn as a dotted line, but the dotted line is coinciding with the object line. You don't draw the dotted line. Dotted line is the back edge, which is coinciding with the front edge of the object. If the cube was slightly turned, not 45 degrees, but let's say 50 degrees or 60 degrees, then you will see the back edge also of the object, which you will draw as a, in the front view, which will draw as a dotted line in that. But anyway, it is coinciding, so there's no problem. That's not a problem. The problem in this particular thing is, it is cut by a sectional plane, okay, cut by some sectional plane, which is not given in the object, in the problem, which is perpendicular to the vertical plane, which means it is, and it is not, it is not horizontal to horizontal plane. It's not parallel to horizontal plane. It is inclined to horizontal plane, such that the true shape of a section is an isosceles triangle with 1.5 inches base and 1 inch height. So what you're seeing on the right side is the given as part of the problem. The cross section is given to you. And what we are now saying is find the sectional top view and front view. So I hope you got the point. Okay? So what we're saying is, this is your front view, right? This is a front view to you. What we're saying that is your cross-sectional plane is inclined to horizontal plane. What is horizontal plane? Is XY line in a front view. In a front view, XY line is your horizontal plane. It is now inclined to the horizontal plane such that the true shape of the section is an isosceles triangle. So which means that let's say the inclined plane is something like this, but you know exactly where it is and you don't know where its angle is. But what is given to you is that whatever it is, the cross section is being seen as this isosceles triangle with 1.5 inches base and 1 inch of height. Yeah, go ahead. Right now, question itself. Okay. Now, if you look at the picture, now you understand what is happening. Which one you draw first, the bottom one or the top one? Bottom one, because you are given the true shape of the cross section. So in the front view itself, you can now draw this line. You can get, how do you get that? Because you know it's 1.5 inches base and 1 inch height. In fact, you draw which one is true one? I'm just thinking. The TS, help me out. This is your
the 1.5 inch will be
1.5 base one. Base is 1. Because why it is like that? Please just think for a second. Two things are given to you, right? 1 inch height and 1.5 inch base. Question to you is, do you get this point, which I'm putting my cursor here? Do you get this point by drawing, by calculating, let's say 1 inch height here? Or do you get these points by saying, where do you have this 1.5? Answer the question.
The 1.5.
Why? Why not 1 inch here?
Because it is tilted to the horizontal plane.
Because
That's
it
where
is.
the actual height and the apparent height will be different.
Please, everyone wants. Thank you. Please, everyone be very clear. Okay. Is this height actual true height or a apparent height of the cross section? And again, look at the base of the triangle. Is it the true length or the apparent length of the triangle? Which one is true, which is apparent? Only that is true can be that dimension only you should use, right? Obviously, if you look at this cross section, it is inclined, right? This is a true cross section, but when you project it here, that becomes a apparent cross section. An apparent cross section, obviously the height is different. So actual this 1 inch height is actually this distance. But that distance I do not know that distance here. But the base 1.5 I know. So I know that this is 1.5 because this remains same. Because that line is parallel to your, it's same in your top view and front view. So I can map, I can find by using a scale, and the scale is perpendicular to your XY line. Find that place where you get this length as 1.5 inch, and there you mark these 2 points. Okay, and if you project it from there, you get your intersection point of your the triangle in the front view. And from this point, if you draw this line, that is your that is how the object will look like in the front view. Okay, any doubts? We'll wait. So this is a reverse problem, right? Here the cross section is given to you, and we're asking, tell us where is your sectional plane, and here sectional plane is this one, and we're asking you to draw the sectional top view, which is this one, and the normal front view. Okay. Any doubts, questions?
Explain the part about the 1 inch height again.
Just to quickly, TS, can you just take out, because maybe you say it in different way. What I said was, we have 2 dimensions here. We need to find where exactly is the isosceles triangle. The cross section is this, right? And the cross section and the plane is inclined to the horizontal plane. That means cross section will be seen in the top view, right? The plane is inclined to the horizontal plane, so the cross section is viewed in the top view because it is cutting the object in the top view. Cutting the object in the front view, but it is visible in the top view. So we need to draw this isosceles triangle in the top view of the object. How do I know this? What is the cross section here? The shape is given, but how do you know where it is? I mean, another way to say that is that this is a true shape of the cross section. I cannot take the triangle and put it here because that is a true shape, but the top view is not the true shape of the cross section. So I cannot simply bring the triangle from the right side. I can draw the triangle, right? It's given, height and base is given to you. I cannot simply bring the triangle here and map it here. I have to take only either the base or the height of the triangle. Which one I should take is a question I asked you. And then I answered saying that this height changes. The true shape is true, but true shape is not parallel to horizontal view. It is inclined. But the base of the cross section, fortunately, is parallel to the horizontal view. So I take the base, which is 1.5 inch, as a true dimension, even in the cross section view of the top view, seen in the top view. So I measure a distance 1.5 inch, which is of course perpendicular to the vertical plane, and that's why this is a vertical plane cup projection. And I measure, keep putting the scale at different locations until I find 1.5 inch here, and that is my base of the cross-sectional view, the triangle which is C. And then this height is not going to be 1 inch. This is not going to be 1 inch. Only in the true projection is going to be 1 inch. Which is 1 inch? Actually, this is going to be 1 inch. But how do you get that? So basically, when you project it back here, and you touch that and you measure it, that is a double check for you. This is 1 inch, then you know your thing is correct. Okay. All right. Okay. TS, in case I made any mistakes, please come and correct me also. All right. Now we will do one more. TA, why don't you take over at this point? I'm just exhausted.
Sure,
Anyone
sir,
here?
sure.
Yeah, yeah.
Yes, sir. Yes, sir.
My water is also. Okay. Yeah, go ahead. You want to take over your projection also? Shall I animate this? Or you
Yes,
tell
sir.
me?
Yeah. Yes, yes. I'll project my screen, sir.
Yes. Good to give a 1 minute break to students also.
Yeah.
All right. Yeah, it's visible. Go ahead. Thank you.
Yes. Thank you, sir. Yes. So this is one other problem where you can just have an rough sketches as you have done for previous problems also. I would like you guys to try just with free hand. It's okay. Give it a try. Yeah, so if you can see here, if you have already read the question, then it is here. You need to find the inclination of the cutting plane itself. This cutting plane. Yeah. So here you need to find the cutting plane inclination with respect to vertical plane. So since this is the top view, since this is the top view and you are able to see the cutting plane as a line, that means that this is an this is a vertical cutting plane. So you should find its inclination with respect to VP. I think many of you can do this in using your mathematical skills within a minute. But then since this is a drawing class, you should use your drawing skills to find the angle rather than maths. However, you can use your maths to just verify your answer anytime, but just don't show it on the drawing paper, those mathematics, whatever you do. Okay, so we'll just proceed for the next one because we have things to cover, and you can always try this when we give you this PPT.
In the previous question, there will be two answers, right? With like the other, if
No.
we join the other two opposite edges,
Mm-hmm.
then that will also give the biggest area rectangle. Like from the point DH and OP, that line.
Yes, yes, you'll get the biggest area there also.
You'll
But
get
then
two
the
answers to this question, I suppose. Yeah.
yes, but when you project it on the front view, what will happen? That area will be very small.
Yes, this will also be
Yeah.
a little small, right?
So let me
Yes.
say one thing here itself. I'm sorry to cut in. Basically, when you choose the cross-sectional plane, no, always choose a plane where you can see a larger projected area. If you have a choice between a
Yes.
smaller projection area, larger projection area, choose one we can see more large because it's closer to the truth. That's all. Okay. Yeah, Jayant,
Yeah.
go ahead, please.
Yes, sir.
Raymond, sorry.
Yeah. Yeah. So that was the point. So we wanted to show most of the things whenever we are drawing an engineering drawing, we are making a sketches. So that's the reason we chose you choose a plane such that you see the most.
Yes, sir.
So that's the reason we have in the very first slide we have showed the cross section of the car. So it should be such that you see most of the parts.
Yeah, but
Okay.
if like a question comes, then the answer is two possible answer, right? So
Yes, yes, possible answers are two. Yes. Okay. So yeah, till now we have seen these are the prisms, rectangular prisms. We have seen the rectangular prisms. Now let us go to pyramids. So we have a square pyramid. Base is of 40 side and axis is 65 That means the height is 65 and the base is 40 And it says that the base is resting on horizontal plane, and all the edges of the base are equally inclined to VP. That means these are the edges. So equally inclined, what does that mean? Equally inclined, that they make 45 degrees. So this is a square. So one makes a 45 degrees, so everything makes a 45 degrees. So that is how you should figure it out. Now it says that there is a sectional plane parallel to HP and bisecting the axis. So this is how the sectional plane data will be given. So one will indicate the angle at which it is, and one will indicate at what distance it is cutting our solid. So now we have to draw the sectional view. That means this is the total height of the pyramid, and the sectional plane will be somewhere here at the midpoint of the height. So this is our sectional section cutting the pyramid. And when you are drawing your top view, you should remove this part, the top part. So this will be the sectional view. So let us see how we obtain this step by step in detail. So I think everyone are now very much familiar how to draw this. We will just project from here and we'll based on how far the axis is from vertical plane, or how far is this point from vertical plane, or how far is the nearest point from vertical plane will be given. However, it is not given in this question, but then it will be given, don't worry. So based on that, you will place the base of the pyramid here, and the rest of the parts we have. These are the edges of the these are the corner edges of the pyramid. Say let us these are OD, OA, OB, OC, and OD. So now what happens when a sectional plane is cutting the pyramid? It will cut the edges at different points. So we label them. First thing we need to do is we should label them. So these are the things: 1 dash, 2 dash, 3 dash, and 4 dash again here. Everyone understands, right? 1 dash, 2 dash, 3 dash, and 4 dash. So this is how the order is. So when you see in front view, 2 dash and 4 dash coincides with each other. So these are very important. You should know which 2 points are coinciding in front view, which 2 points are coinciding in top view. Those are very important thing, because you will know you in later examples why is it very important. So yeah, now let us see how we obtain each and every point. So we see that O1 O dash A dash. So let us say O1 dash A1 dash. Don't worry about the nomenclature, because here we have already used O, A, B, C, D. We are now using O1, A1, B1, C1, D1. That's all. Don't worry. And if you have to go for another drawing, then you can use O2, A2, B2, C2, D2 like that. We'll see that also. So now this O1 dash A1 dash is the true length of the edge. Why? Because this OA here, everyone can see OA is parallel to our vertical plane. So that means in front view, we can see the true length of the line, whatever it is, the edge of the pyramid or axis of the pyramid, be it anything. If it is parallel to vertical plane, you can see the true length. So this is the true length of the slant edge. So now what happens is it is cut. The sectional plane is cutting this edge at this point. So you can bring this projector straight away down, and you can meet this line OA, and then that point is our point of intersection of the sectional plane and the pyramid. So now you obtain 1. So similarly, you obtain 3 also, because this is also the true height. But then there is this edge, O1 dash, B1 dash, or O1 dash, D1 dash. These two edges are not parallel to our vertical plane, but then they are somewhat inclined. So for these edges, what do we do is we project this line here. We wanted to know at which point it is intersecting. So at which point it will intersect, to know that we project this line here, and we say that, acha, okay, this is the point where, this is the distance from the center at which it is intersecting 2 dash and 4 dash. So that's why we project here, we bring it down, and then with this as a radius, here there is no O1 written, but then you have to imagine that the center point here is O1. So from O1, you should take this radius and you should cut this arc here and here, and that is how you get 2 and 4. I hope everyone understands why we are taking the arc and cutting. If anyone has a doubt, you can bring it up.
Can you explain it again, the arc thing?
Yes, sure. So here what happens is, see, from 1 dash, you just brought down the projector and projection line, and then it is cutting our O1 A1 at this point, and we have labeled it as 1. But then how do we get 2 and 4? We can't bring down a projection here and make it intersect our edges, because it is this vertical projector will be coinciding with our O1 D1 and O1 B1. So we don't know where it is intersecting exactly. So that's why what do we do is we take how far from the center is this actually intersecting. So when you see from the top, so we come to this figure, when you see from the top, you know that the sectional plane is cutting this plane somewhere. So when you know how far is it intersecting the edges, how far it is cutting the edges, then you can just cut an arc and say that it is intersecting here. So here for 2 dash and 4 dash, you are not able to see how far it is intersecting. So that's why what do we do is we draw a projector here towards the right or left. Anyway, towards the left or right. Anyway, any side, whichever side it is fine. Or here what you can do is, since all edges are same and the sectional plane is exactly parallel to our base, it will be intersecting all the edges at the same distance from the center. So you can straight away have 1 and 3, and then you can make a circle like this. Or if this base is having different sides, then it will intersect at different points. So that time what you have to do, so you have to draw this horizontal projector, get this point. From here you have to draw a vertical, get this point. Now taking this as a radius, O1 1, or say this is being 2 dash, you can take this also 2 dash, and here bring it as 2. You can label it as anything, whatever you want, and then O1, 2, and then cut the arc on O1, D1 and O1, B1. Cut a couple of arcs, one above and one top, because there are 2 points, 2 dash and 4 dash here. So cut a couple of points, and then those points are 2 and 4. So just a minute. Yeah. So nomenclating these things, how do you know that this is 2, this is 4? It can be 4 here and 2 here. You should go in a manner. See, you have labeled A, B, C, D. So I'm labeling 1, 2, 3, 4. So that is how you have to label.
Okay.
Now is it clear? Now is it clear, everyone?
Yes.
This is a very important thing. This is a very simple example, but whatever this is a very important thing.
I
Taking a
have
horizontal.
I have a
Yes,
small
yes.
doubt. Like as sir said that the section lines have to be at 45 degrees. So here they are horizontal.
45 degrees. Sorry.
Sir had said that those section lines have to be 45 degrees with respect to the drawing sheet. But like here they are drawn horizontal. The section lines are like in the cross section.
Acha, this one. Yeah. See, these are already 45 degrees. So we just wanted to show you the difference. So that's why we have made it here like that. These things are already 45, no? This one and this one.
Yeah. So like do
That's
we
why
have
we show that's why we showed you in a horizontal line, but don't worry, it should be 45 degrees. Yeah.
okay. Fine.
Yes.
Thank you.
Yes. So if there are no more doubts, we'll proceed. Yes. So this is another example. The same thing. A pyramid position is the same, but then it is now we have a sectional plane perpendicular to VP and inclined at 45 degrees to horizontal plane. We have seen a sectional plane which is exactly parallel to horizontal plane. Now it says that it is inclined at 45 degrees to HP. See. So just give it a try. I'll give you just half a minute or 1 minute time. Just give it a try.
Unknown caller.
Yeah. So we'll see how is this cross section. Yeah, so it is said that it is inclined at 45 degrees to horizontal plane. That means this 45 degrees, it can be seen in front view only. So now this is the sectional plane, which is at 45 degrees. Now it's intersecting at 1 dash, 2 dash, 3 dash, and 4 dash. So in the similar fashion, we'll draw the projector here, and get 1 and 3. So to get 2 and 4, it is the same method which I have taught you. Draw the horizontal. Now see, you just label this point with respect to this, to 1 dash. And we draw horizontal. We draw a vertical projector. And then taking this as the radius, O1, 2, 1. So this is 2, 1 dash, so this will be 2, 1. O1, 2, 1. And cut the arc above and below. Now this will be our top view of the cross section. Everyone get it? Yeah. So now, how do you draw the true shape of this? So this section is here. It is at 45 degrees. So when you choose an auxiliary plane here and draw auxiliary plane at 45 degrees, then when you project it, you will get the true shape of it. So it's simple. You just project it like this and take this distance here and take this longer distance here. And you'll then label like this 1, 1, 2, 1, 3, 1, 4, 1. And you get the true shape of the sectional plane, whatever it is. So that is how you get the top view of the cross section and true shape of the cross section. Okay. So if there are any doubts, we'll take up, or else we'll move to the next one. Because there are a couple more very important examples which we have to see. If there are no doubts, we'll proceed. Okay. So this is also a similar pyramid thing, but then see in this the pyramid is resting on one of the corners in horizontal plane, and its axis itself is making 50 degrees with horizontal plane. That means here in the so far we have seen that the axis is perpendicular to the horizontal plane when it is resting on the HP. Now it is making 50 degrees with horizontal plane and parallel to VP. That means this axis now has to be tilted towards this side or this side. You can take any way, and it has to be at 50 degrees with the horizontal plane. And it says that there is a cutting plane perpendicular to VP and parallel to the base. So that means it's just like this. It will be absolutely parallel to XY line. So that is not a problem. So see, this is the first thing we need to do. We need to rotate our pyramid. Yeah, this is the, okay. Yes. So the cutting plane is parallel to the base. So for first thing we need to do is we have to rotate the pyramid, and then this is the base. Now the cutting plane will be absolutely parallel to the base, and it is bisecting the axis. So this is the axis, and you have to bisect the axis here. So now first thing when you rotate the pyramid is you should get the positions of the base in top view, right? So for that you need to just tilt it and then draw the vertical projections here and draw the horizontal projections from here, and wherever they are meeting, that those points will be the respective points. So respective points, what does that mean? So you are extending from B1 D1 here, this point, this line, let us see this one. You are extending from B1, D1 here, but you're drawing a vertical projection, and you have a horizontal projection from D here. So wherever these both meet, it will be D1. And you have a horizontal projection from B. Wherever these two meet, it will be B1. I hope everyone gets this. So similarly, C1 also.
What is the other vertical line, like just besides this B1 D1, like at a very small distance?
Yes,
What is that? Okay, that is the
it's
intersection.
actually from this section.
Ah.
Yeah, in the next figure, you will see that. Yeah. So this is a point where the sectional plane is cutting this edge, E1, A1, E1 dash, A1 dash. So from that point, when you take here, this is the point. This is the point where the top in top view, this E1, A1 edge. This is the whole edge, E1, A1. So this point is a point where sectional plane is cutting the pyramid. So let us label it as 1. So that is where is our 1. So in this example, what happens is from this edge, you can draw a vertical thing, and let us say this is point 1. And this edge, we have a vertical projector, and it meets our E1, C1 at a particular point, and we can see this is 3. And again, from this point, this is our 2 dash and 4 dash. So we can draw a vertical from here also, and it meets our E1 D1 at a particular point and our E1 B1 and at a particular point. So in this example, you need not take a horizontal thing, draw a projection and take that radius and cut an arc. That procedure is not needed because this point is this projector is not aligning with the edges. It is intersecting the edges at a particular point. So that's why you get 2 and 4 straight away. So that is where you will have your 1, 2, 3, 4. Right? Everyone understands this? Okay, let us proceed. So this is our cylinder. We have seen pyramids. Now let us see cylinders. This is a very important thing because for cone, there is another example of cones. For that is also understanding cylinders is very important. So what do we do is for a cylinder, basically, so the cylinder is resting on the horizontal plane. So when you see the top view, it will be a circle, and when you see the front view, it will be a rectangle, and when you see the side view, also it will be a rectangle only. So yeah, now this circle you should divide accordingly. Like you can divide it into 4 parts also. Just 1, 2, 3, and 4. Matlab, each sector having 90 degrees. But then you will get a very bad answer. So minimum you should divide it into 8 parts. That means each sector should be 45 degrees. Minimum. So then only then you will be able to get the perfect. Here it is divided into 12 parts. Accordingly, it is labeled, and labeling is a very important thing. We'll see why it is a very important thing. So see, there is our sectional plane perpendicular to VP and inclined at 45 degrees to our HP. That means the inclined plane is somewhere like this. Okay. Yes. Okay. Now see the just focus on the labeling as of now. We'll see how it is how the sectional view is obtained later. So this is one in front view. It happens. This happens as 1 dash, and let us say this is also 1 dash. Okay, both of them will be coinciding. So we say this is 1 dash and this is also 1 dash. And similarly, what will happen? This is 2, so it will be 2 dash, 3 dash, 4 dash, 5 dash, 6 dash, 7 dash. Now what happens? You should come back again. 8 dash, 9 dash, 10 dash, 11 dash, 12 dash. And this is again 1. So this is how the labeling goes. Now let us see from side view. So here is the side view. What happens when you see from this side? When you see from this side, what happens? The leftmost part, what you see is 4. So this is our 4 dash. And then what do you see? 3 dash and 5 dash will be coinciding here. And then what will be the next point? 2 dash and 6 dash. And the next point will be 1 dash and 7 dash. Yeah, and the end rightmost point, what is the rightmost point when you see from this side? It will be 10. That means here it is 10 dash. So this is the labeling. First thing what you need to do is labeling. So now there is a sectional, like there is a section like this. So this is the section. And now what you have to do is label each and every intersection of our sectional plane and the generator. So say, let us say these are the lines, generators. Why I'm calling it as generators? Because in cone, they are called as generators. The slant height is called as a generator. No, you just you have one generator and you rotate it about the axis, you get the cone. So that's why it's called a generator. So let us call these also as generators. So you label every intersection point wherever this generator is intersecting with our sectional plane as A, B, C, D, E, F, G. It's not mandatory key you label them A, B, C, D, F, G only. You can label whatever you want. But then what happens is there is this particular generator. Let us consider this point. Here we have written as C dash and C1 dash. Let us see why it is why so. So when you draw a vertical here, what happens? This is the point. No, we have 3 here. This is the same thing, 3. So this generator which is at 3 is intersecting our cross-sectional plane at C. So these two coincide in our front view also. That's why we label as two things, C dash, C1 dash. This you should be aware. While you are labeling itself, you should be aware that our cross-sectional plane will touch the cylinder at 2 points when you see it in a front view. So that is why you should label it as two things, C and C1 dash, C1 dash, C dash and C1 dash. Okay. Yeah. So similarly, you'll have two points at each and every point, but then see here the leftmost part and the rightmost part, there are only one, A dash and G dash. Why? Because there is only one generator now here. A and G, there is only one generator. That's why we have only one point, A dash, G dash. But everywhere else, this one line indicates there are two generators, one in the front, 2, and one at the back, 12. So that's why you have two points. So now once you understand this concept, it is simple. You just draw the horizontal lines from in this intersection point to the side view line, and then you get the point. So let us see for the point C dash. So this C dash is intersecting our generator. Which generator is this? It is the third generator, third one. So there is a point here of point of intersection. Now when you project it horizontally, you should meet that horizontal projector at 3. There is 3 na here, so there is 3. You should meet that horizontal should meet the vertical generator here at the same generator, 3 dash and 11 dash. So where will that be? This is 1 dash. So this will be our 2, this will be our 3. So it will meet somewhere here. So it's going and it's meeting here. And the same thing you have to extend this also, and it will meet our 11 here. You can see here. So this vertical generator is our 3 and 11. So it will meet it's 3 and 11. So you have to extend this point here, and it will meet 3 at a point, and then it will meet 11 at a point. So those 2 points are our C dash and C1 dash. So here when you label it, you should see that what labeling you are giving. Either you are giving C dash to with respect to 3 or with respect to 11. Here we gave it with respect to 3. C1 we gave with respect to C. with respect to 3, sorry, C1 we gave it with respect to 3. So here also we have to label C1 dash with respect to 3. So each and every point you have to intersect accordingly. Understand? And once you get all the points below and above, you just join with your free hand. This is a circle. That doesn't mean your side view will be a circle. It's just coincident, that's all. You should join these all points with your free hand. Now everyone gets it? How to get the side view of the cross section. So the top view, the top view is very simple. If you cut this in any direction, you see circle only. So that's why it's just the circle. And labeling is a very important thing. You should do it in a particular fashion. So now you, to get the true shape of the section, you take an auxiliary plane and you get the true shape of the section.
Okay, Revant.
Yes, we'll go
Finished?
ahead. Yes. This is the last example.
Because
Yes.
7's 5 and 7, like, yeah.
Yes.
Repeat.
I think I need not speak much about this. I have spoken enough about the cylinder. Now this is a very similar fashion. Now there is only one difference between a cylinder and a cone. What is that? Here you can in top view you will get a proper section. It's not like a cylinder key, you only get a circle. The section, you get a section here, but rest everything is as it is. So how do you get a section here? There are a couple of ways to get the point. You observe these points D1 and D. These are the points which are on the exact coinciding line. So to get these points, either you can follow the arc method, or you can get the side view point, and then draw a vertical here and then project it like this. Understood? I hope everyone gets it. One is the arc method. You can follow the direct arc method to get these points D1 and D, or you can first get the side view of the cross section, and from there you can draw the projection lines and get the top view. That's it. Everything is same as cylinder only. Okay, so we conclude our meet. So these are just the points which have, whatever we spoke, these are the same points. You can refer them later on when we give you this PPT.
Thank you, Revant.
So I have a doubt in the cone question. Why isn't the section in the center in the bottom left, the top view?
Yes. Let me bring this up. Yes, what can you repeat your question?
Why isn't the section in the center in the top view?
Acha, it's because the sectional plane is inclined. It is inclined at 45 degrees here, VT. So on the right side, it will intersect at the higher point than the left side. So left side, it is nearer to the base. See, left side is nearer to the base and right side is far away from the base. So that is why it is. This is not a circle though. If you are confused if this is a circle, no. These are all the points you get from projections. See, there are these vertical projections from each and every generator, and they intersect the top view of the generator, and then you label them accordingly. If you take this, if you take this point as G, you should take this point as G. I mean G dash G. If you take this point as E, then you draw a projector and you get E1, E. Then you draw, draw with free hand and join all these points to get the top view.
Okay, yes, got it. Thank you.
Yes, yes.
Okay, so we can close the meeting right now.
Yes, yes.
Thank you, Revan, and
Yeah.
thanks, Professor Ravi.
Yeah,
See
thanks
you
everyone.
everyone in the lab.
Yeah,
Yeah,
see
see you
you next
everyone in the
time.
lab.
Okay. Go ahead, Prabhat.
Yeah, thank you. Thank you.